Swayam Prabha. Digital India. Educated India.
So we looked at graph degrees. And there was a small toy puzzle kind of a thing that I posed to you. Let's discuss that. It's actually not a toy puzzle. It's a very neat counting argument, right? Construct a triangle free graph on n vertices of maximum cardinality of U. Right. So this was a question that we stopped with in the last class, right? And we saw that what is the maximum possible? Is it at least n square by 4, at most n square by 4? Is it exactly equal to n square by 4? No, but if you construct a graph which has n square by 4 edges, then should the maximum be at least n square by 4 or at most n square? Okay, let me repeat the question, right? So the question is, the goal is to maximize the number of edges, satisfying a certain property. The property is that there should not be any triangles. Somebody comes up and says, look, here is this graph, n is even, I put n by 2 edges here, and I put n by 2 vertices here, and put all these edges. In graph theoretic notation, this graph is called k n by 2 comma n by 2. Right? So obviously the number of edges that you see is n square by 4. Now, is the maximum at least n square by 4 or at most n square by 4? Remember, you want to construct a graph and maximize the number of edges but no triangles. I show you one. So is the maximum greater than or equal to this or lesser than this? Okay, maximum has to be greater than or equal to this, right? Imagine the set of all graphs. So how do you avoid this confusion, right? It's a simple confusion, right? How to avoid this confusion? Imagine this set, right? What is this set? This set consists of graphs on n vertices, right, which have no triangles, right? This is the graph, this is the set, right? In this set, I show you one special graph, and I show you that in this graph, there are at least n square by 4 edges. What is the value of the maximum in this set? It's at least n square by 4 because of the property of the maximum. No, if I show you something, maximum can only be at least as large as that. It can't be smaller. So not at most, it's at least. Fine. Okay. So that's an easy part. Fine. Now, what do you think? You think this is this number n square by 4? Can you improve it? Can anybody try to improve it, or give me a proof that you can't improve it at all? You can't improve, so how would you prove it? Right? Right? Okay, that's a good thing. So let me try to take this graph. What he says is that this is the rhombus. Okay, 4 vertices. 4 vertices and no triangles till now. Right? So n square is 4 square is 16 by 4. Yeah, yeah. Yeah, where will you add an edge? Anywhere you add an edge. Right? Right. In the rhombus it is clear. But maybe I have a different graph. right? No, that's a good thing. Maybe I have a different graph where I can do n square by 4 plus 1. But that idea is a good idea. So let us convert that into a proof, right? So often the trick in all these businesses is to actually, when you do a logical argument, the intuition is what your eyes see and what your brain actually imagines. But when you do a logical argument, you cannot use intuition. You have to bring in the correct variable so that there is no ambiguity, right? So let us try to use this argument, right, in a logical way so that there will be a gapless proof, right? It will be a complete argument, right? So therefore, let us write down the claim. Okay, so let me try to erase this first. Okay. So claim, let G be a n vertex triangle free graph. Then the number of edges in G is less than or equal to n square by 4. This means that you can't do better than that particular graph, right? That graph seems to be the graph that achieves the optimum. Right? Of course, there are other questions. Is that the unique graph? Are there other graphs? Those are all puzzles that you can play with, right? And all these puzzles have major applications throughout the scientific world. They just don't remain as small toy puzzles. Okay, right? Okay. So now, how does one do this proof? The proof is that remember that we have taken a triangle free graph. There is no triangle, right? So let's write down the proof. Select U to be of maximum degree, right? And this is a cleverness, and this cleverness comes by practice, right? So let us say the maximum degree has value k, just that we need a symbol, right? Some notation. So now U looks like this. These are k neighbors, right? And here is the rest of the graph, right? So which is, this is called n of U, and this is V minus n of U, right? So what do we know? Because the graph is triangle free, there are no edges here, because if there were edges, then there would be a triangle, right? So now let us give names so that our calculation is unambiguous, right? So therefore, let us call, let us consider the graph to be partitioned into two sets, right? This is n of U, right? And this is V minus n of U. Right? That is the third step in the logical argument, to argue that there are only n square by 4 edges, right? Now we know that there are no edges inside n of U. What is the degree of every vertex here? Correct, k, right? Less than or equal to k, because somewhere U is sitting here, U is not here, right? And U is a vertex of maximum degree, right? And there are k vertices here. Okay, therefore, the size of this set is equal to n minus k. So what is the total number of edges in the graph? Very good. Is it less than or equal to, or at least? Wait. Is it less than or equal to, or at least? Because I would always like to write all the statements completely with the correct inequalities. Because see, you want to prove this guy. You want to prove less than or equal to. Right? So we cleverly now picked a vertex. It is triangle free. No triangles here. We partition the vertex sets into two groups. This is one partition. This is the second partition. Second set in the partition. Right? There are exactly k vertices here, there are exactly n minus k vertices here. Right? What is the degree of every vertex in the right hand side partition? At most k. at most k. Are there any edges inside the first partition? Let me give names to this. I forgot that you can't see my, yeah, L and R. Inside L, are there any edges inside L? By design, there are no edges inside L, because if there is an edge inside L, along with you will get a triangle. There are no edges. So where are all the edges? All the edges are here or here. Fine. So every edge has at least one endpoint which is from R, and the degree of R is less than or equal to k. Therefore, the total number of edges is less than or equal to the total number of vertices on the right hand side, which is n minus k, multiplied by k. It can't be more. Now we have not finished the proof. Our friend there might think we have finished the proof. There is one step. Why should you set k equal to n by 2? That's good. So at least from the right hand side you've got the pattern, right? And now you've got n minus k into k. But what is the correct claim to make to finish? That's a good thing, right? So don't try to fix the proof to make your argument, right? So then you will make mistakes, right? You are trying to somehow get n square by 4. But there is something else that you should observe, that the right hand side function n minus k multiplied by k is maximized at what value? School calculus, at n by 2, right? You can do calculus, but let me show you a different argument, right? It's a very formal argument. This is k and this is f of k. So consider the two functions f of k is equal to k and f of k is equal to n minus k. What does f of k equal to k look like? F of k equal to k is an increasing function. It looks like this. Maybe I didn't draw it properly, but you can fix the slope. And as k increases, f of k equal to n minus k is a decreasing function. Right? Where does it attain the largest product? At this point. At every other point you can basically say that the inequality is less than or equal to the value at this point. Okay? So therefore, at k is equal to n by 2, this function is maximized. Therefore, number of edges which is less than or equal to k into n minus k. Very importantly, don't miss that k into n minus k is completely a formula which involves graph theoretic parameters, maximum degree into n minus maximum degree. But now we observe this very interesting property that this number, by using non-graph theoretic mathematics, right, just using inequalities or using calculus, this is less than or equal to n square by 4. Right? So we have used two different arguments, right? Two different observations. One is completely graph theoretic, right? So what was completely graph theoretic? We picked a vertex of maximum degree. We said there are no edges in the neighborhood, right? Then we came up with counted all the edges, that is k into n minus k. Then we said k into n minus k is at most n square by 4. Okay? So therefore, this completes a very simple proof, again based on the degree alone, plus some additional properties. Right? Let's do one more problem, right, again about the degrees, which is from the textbook by West, right, which is unrelated to the previous problem, right. So it's a completely new thing. What I'm showing you is that you can extract so many interesting properties just by looking at the degree. Remember, that was my theme. I said if you look at a graph, if you go to a city, you know that, oh, at this circle I saw 4 roads, at that circle I saw 2 roads, and so on. Just by keeping track of this information, you can extract all kinds of structural information. First one was, if the degree was very high, then the diameter is low, which means the furthest pair of vertices is at most 2. Then I showed you that there is a possibility that the degree is very low, but the diameter is also small, it is log n. Right? Then I am showing you that if if the graph is dense enough, right, then you will definitely have triangles. If the graph is dense enough, which means it has many edges, then it will surely have triangles. Right? So essentially we are just playing with degree alone. So let's look at this one. Here is another claim. Any graph on at least two vertices I mean, will people believe you if you say this? You walk into Coimbatore and somebody says, there are two circles here which have the same number of roads going out. Right? Of course, it is very natural because there are four and too many circles are there. I mean, you can use pigeonhole principle. You can say that Coimbatore has maybe 50 intersections. Every intersection has at most 5 roads, right? But there are 50 intersections, therefore there must be at least 2 intersections with the same number of roads, right? But how do you know this is true in any graph? Right? Let me make it more. So if you look at the internet, which is all lot of network elements, routers, switches, and all these things, right? If somebody says that there are at least two network elements which have exactly the same degree, kind of looks like a very mysterious fact, right? Why should it be true? So why is this true? If you take NC2, right, n into n minus 1 by 2 is always even, but all the numbers are different, no? You are talking about the sum. I am counter arguing, saying the sum does not contain information about the distribution, that is about two specific values. I am telling you that if you take the sum, why did you not take the sum of 1, 2, 3 up to n? It is n into n minus 1 by 2, it is even, and there are no two elements which are the same in your summation. So the sum doesn't contain enough information. So often this is the trick in the logical arguments. You must not focus on only the statement. You should focus on everything that is around the statement. So let me help you discover the statement completely by yourself. Right? He wrote actually the second observation. The first observation is number of vertices is equal to n. Right? Degree, right, is greater than or equal to 0 and less than or equal to n minus 1. I should have written it better, but let me try to use the eraser and dv is less than or equal to n minus 1 . Range of n values. Now I have set up enough for the pigeonhole principle, right? So there are, the vertices are n pigeons, right? And the degrees are also n, right? So if it turns out that all the degrees are distinct, what does it mean? Why maximum n minus 1? It can take 0 also. So therefore there are only two cases. Have same degree, right? Or in this case our work is done, our claim is correct. Or in our thought experiment you say that all vertices have different degrees. Right? So which means V1 has degree 0, some V2 has degree 1, and here is where your pigeonhole principle is used, right? All of them go into different holes, right? So therefore in every hole there must be one, because n pigeons are there and n holes are there, right? But if one vertex has degree n minus 1, it is adjacent to everybody else, so the degree 0 is not possible, so the second case is not possible, right? So therefore there must be two vertices of the same degree. Right? Like I said, it is a toy, but as you can see that it is not trivial, right? So it is all puzzles, right? and if you have to complete the puzzle, you have to make so many intricate observations, though the end result is only something, it looks like not so important, right? But many of these things put together give us a very fundamental understanding of many subjects. Okay? So now from these puzzles we'll make one big jump to a very, very interesting result.